Hi everyone, welcome to my talk on solving the anisotropic eikonal equation using physics-informed neural networks. I would like to begin by acknowledging my co-authors Ehsan Haqiqat and Tariq Al-Khalifa for their contribution to the work. In this talk, we will see what are the benefits of using neural networks to solve the anisotropic eikonal equation and what are the challenges that need to be addressed and solved in the future. So let us get going. Fast and accurate travel time computation, as we know, is essential to the success of many applications, including statics and move-out correction, travel time tomography, and ray-based migration. And moreover, since many of the actively explored areas in the world exhibit seismic anisotropy, our travel time computation algorithms must take into account this anisotropic nature of the Earth. And there are several algorithms that have been developed over the years to solve the anisotropic eikonal equation, but two popular approaches include ray tracing and numerical solution of the eikonal equation. Now, ray tracing has some issues with regards to expensive interpolation that it requires for imaging applications, and often it has this problem of shadow zones where rays may diverge from one another, leading to empty areas with no travel time values. Therefore, a lot of attention has been paid over the years to solve the eikonal equation numerically. However, the main challenge associated with numerical solution of the anisotropic eikonal equation is due to the high-order nonlinear terms that it contains compared to the isotropic case. During my PhD years, I was involved in the development of an iterative fast-sweeping algorithm based on fixed-point iteration to account for the effect of these problematic high-order terms. And therefore, in that work, what we did was to take all the high-order terms on the right-hand side and then account for their contribution in an iterative manner, where in the first iteration you ignore those terms and you slowly bring the effect of those terms during the next iterations. Le Boutier et al. In 2019 proposed a discontinuous Galerkin discretization-based fast-sweeping method also to accurately solve the anisotropic eikonal equation. However, one thing that's common with these algorithms is that even for small perturbations in the velocity model or source location, same amount of computation is needed. Therefore, for example, if you have several thousand sources, for all those sources, same amount of computational effort is needed. And if you have if you're doing seismic inversion, you have an updated velocity model, you need to start all over again. Therefore, any information gained during computations from the previous sources or previous velocity model is not utilized in such algorithms. Therefore, we look into the machine learning literature to seek an alternative approach that could help resolve this computational bottleneck in such scenarios. Now, there is no doubt that deep learning is fast emerging as a potential tool to tackle long-standing research problems. Recent advances in the field of scientific machine learning have demonstrated largely untapped potential of deep learning for scientific computing as well. And it is to be noted that that the idea to use neural networks for solving a partial differential equation has been around the 90s. However, due to recent advances in the theory of deep learning coupled with a massive increase in computational power and efficient graph-based implementation of new algorithms and automatic differentiation, have seen a resurgence of interest in neural networks to approximate the solution of PDEs. And recently, the paper by Maziar Raisi et al. Got quite popular, in which they proposed a physics-informed neural network framework to solve partial differential equations. In short form, it's known as the PINNs. And since then, several applications of PINNs have emerged for a multitude of problems in science and engineering disciplines, solving many equations across the disciplines. Now, in this work, what we are going to do is we are going to look at how PINNs can be utilized as a framework to solve the anisotropic eikonal equation, and what are the advantages and disadvantages of doing so, and are there any challenges that remain to be addressed in this framework. And therefore, here is an outline of things that we need to first understand before we can see how PINNs can be applied to an isotropic eikonal equation. And I'll go over them one by one. And once we have all the pieces of the puzzle, we'll put the pieces together really to understand how we can solve the anisotropic eikonal equation using PINNs. The first thing that we need, of course, is the anisotropic eikonal equation. For simplicity of illustration, here I show the VTI eikonal equation in 2D. What we see here is, for example, the unknown travel time field capital T. We also see the vertical velocity v, and we have the anisotropy parameters epsilon and eta. So what we hope for at the end of solving this equation is to know this unknown travel time field capital T, which we see here in the form of spatial derivatives here in this equation. Now the second thing that we need is a feed-forward neural network. Now a feed-forward neural network is essentially a set of neurons organized in layers in which evaluations are performed sequentially through layers. So what we have in a feed-forward neural network is an input layer, an output layer, and a bunch of hidden layers. So for our problem of solving the anisotropic eikonal equation, our input will correspond to the spatial coordinates x and z in 2D, and if we have 3D problem, there will be 3 inputs needed. And we have one output neuron that will tell us the travel time at that particular spatial location. So again, on the inputs we have spatial locations x and z, on the output we have the travel time at that location, capital T, as a function of x and z. So this is essentially a simple feed-forward neural network that we use. And regarding the hidden layers, we will use an arbitrary number of hidden layers, and it will be a problem-dependent thing. Depending on the problem you're solving, we may need to increase or decrease the number of hidden layers, which we will see in a while. All right, so how can neural networks be used really to solve a PDE? So essentially this boils down to the universal approximation theorem, which says that a neural network with a single hidden layer and a finite number of neurons can represent any bounded continuous function. Now, while this is true in theory, in practice it is often hard to find the parameters, which is the weights and biases of a neural network, really to approximate some complicated functions. However, this strong representational power of neural networks are well known since the late 1980s. Therefore, essentially what we are hoping for is somehow to get to a trained neural network that, when we input the spatial coordinates x and z, gives us the travel time field t, x, and z. So how to do that? One important component to understand that is automatic differentiation. Now, to solve a PDE using neural network requires, of course, derivatives of the network's output with respect to the input. So remember, the output is travel time, the inputs are the spatial coordinates, and therefore, if you remember the equation, we had the spatial derivatives of travel time, and therefore we need some mechanism to get those derivatives. Now there are many ways to compute those derivatives, such as symbolic differentiation or finite difference approximation, but we use something called algorithmic or automatic differentiation. Automatic differentiation uses exact expressions with floating point values instead of symbolic strings and involves no approximation error. While there are many advantages of automatic differentiation over symbolic differentiation or something like a finite difference approximation, but in practice it is often hard to write an efficient implementation of automatic differentiation. Thankfully, many existing computational frameworks have made available efficiently implemented AD libraries, so that's a positive. And those of you who are familiar with neural network training would know backpropagation, which is a generalized technique of AD. So backpropagation is essentially something very close to AD, or a subset of automatic differentiation. All right, so now putting these pieces together, how can we solve the VTI eikonal equation? In short, the way we solve the anisotropic eikonal equation is by training a neural network to minimize a loss function, this loss function which is formed by the VTI eikonal equation. So let's go in and try to understand what this loss function contains. So the loss function contains 3 terms. The first term here tries to minimize the residual of the VTI eikonal equation. As you can see here, this italic L represents the residual of the VTI eikonal equation. So therefore, one thing that we need is, on a bunch of collocation points, x star, we want that our neural network to minimize this residual. So therefore, if we input these coordinates x star, our network should be able to give us some solution which would give us the minimum of this function here. Another term that we have in our loss function enforces positivity of the solution, and therefore we don't want all the solutions that minimize these residuals, but we want solutions that are positive, because travel times must be positive. So that's a constraint that we need to add. Another constraint that we have is that the travel time at the source location must be 0. That's of course a boundary condition that we need to add, and combining all these three equations form the loss function of the eikonal equation. So therefore, what it boils down to is a minimization problem that you see here, where we want optimal weights of a neural network theta, such that they minimize this function, this loss function j, over these collocation points or training points x star. Now, there may be a few things that are confusing here. I think they will become a bit more clear with a pictorial summary here. So this is a workflow how we can solve the anisotropic eikonal equation using physics-informed neural network. So let's kind of summarize everything here in this picture. So what do we have here now? First of all, we select some training points, x star, z star, from our domain, and we input it to a randomly initialized neural network, right? So we initialize our neural network randomly because we don't know the optimal weights. Now, what would a randomly initialized neural network give us as output in terms of travel times? It would give us some garbage, right? Because the neural network has not been trained to give us a solution that we are seeking, and therefore it comes in the optimization process. And therefore, we want now this neural network to go back and update the weights such that this loss function j is minimized. So it has to. So we are asking the neural network to go back and tune the weights and biases such that the loss function that we saw in the previous slide is minimized, which is formed with those three terms. And at this stage, we need to provide the velocity and the anisotropic parameters as well to the optimization function, and therefore they are tied to this optimization problem. And once we are done with our optimization process, and once the network is trained, this gives us a trained neural network. And now how do we get our travel times in the end? Is now we feed coordinates corresponding to a regular grid, and it gives us travel times on a regular grid, which we can use for seismic imaging. Now, some of you who are used to neural networks in something like supervised learning approach would kind of maybe feel confused that, okay, where is okay, we see the training is going on, but where is the label set? Actually, there is no label set here. In fact, we are using a loss function as something that guides the optimization process, and therefore this thing needs to be clear that there is no need for a label set here in this case. So therefore, there is no need for data set that needs labeling, etc., as we do in standard computer vision problems, for example. But here it's kind of a different way of using neural networks. So this is through the loss function. The loss function contains the partial differential equation, and therefore now if you talk about TTI eikonal equation or the orthorhombic eikonal equation, solving them is pretty straightforward with this approach, because in the loss function you just replace the VTI eikonal equations base residual to the TTI or the orthorhombic case, and therefore this method can be applied to anisotropic models with even lower symmetry and more complicated equations. All right. So now let's test our proposed algorithm and show some of its interesting features on different synthetic models. The first one that we have is a homogeneous TTI model. So we choose a model of size 1 by 1 kilometer square. We choose a vertical velocity of 2 kilometers per second, an epsilon of 0.2, an eta of 0.083, and tilt of 30 degrees. Now what we're going to do is we're going to place a point source in the middle of the model at x equals 0.5 and y equals 0.5 kilometers, and we are going to compute travel time solution using PINNs. And what we are going to do is we are going to also compare that solution with a regular fast sweeping method, and we are going to compare that with a reference solution which is computed using a high order fast sweeping method. But before I can show you the results, there are several hyperparameters for this neural network or the PINN model that we need to sort of tune before we run the algorithm, and therefore in this case we are using a neural network with 8 hidden layers and 20 neurons each. The activation function that we have is arctangent for all the hidden layers, while the final layer is linear. The learning rate is 0.001, and we use an atom optimizer with a batch size of 256. Alright, so here are the travel time errors for the homogeneous TTI model. So what you see here is, this is the source location, and what you see here is the travel time field. This is the, let's say, the x-axis, this is the z-axis, and here are the absolute travel time values. So in the case of physics-informed neural network, you see that the absolute travel time values are almost half of those we see in the fast sweeping method, and therefore we can see that the accuracy of PINNs is really comparable or even much better than a regular fast sweeping method. And now if we plot these travel time contours, what we see here is in black is the reference solution, in blue is the physics-informed neural network solution, and in red, dotted red, is the fast sweeping solution. So you can clearly see in the direction orthogonal to the symmetry axis, there are a large amount of errors in the fast sweeping solution, as we saw in the previous slide. All right, so this was just a homogeneous TTI model. Let's see how the PINN algorithm can perform on more complicated models. All right, so now we do is we take the vertically varying TTI model, and which has a dimension of 1 by 1 kilometer square, and the velocity is linearly increasing. So at 0 depth, it has a velocity of 2 kilometers per second, and increases up to 3 kilometers per second at the depth of 1 kilometers. The epsilon has a value of 0.2 at the top and increases to 0.4. The eta parameter has a value going from 0.083 to 0.167, and tilt goes from 30 degrees to 50 degrees. And now what we are going to do is we are going to change the location of the source. And this is because we want to see if we can use an already trained neural network from the previous models. That is, the previous model, the homogeneous TTI model. Now we already ran the training in that model. Now can we initialize the neural network for this vertically varying TTI model with the trained model, and will it help? So this is essentially something called transfer learning, which is very popular in machine learning, in which you transfer the knowledge you have gained by solving one problem into the other problem. And this is what we get. So here's the loss function. The one in the blue is for the homogeneous TTI model that you saw before, and this one in the orange is the vertically varying TTI model. As you can see, by randomly initializing the homogeneous TTI model, it took plenty of epochs really to converge. It was pretty slow compared to the vertical varying TTI model, which started with the already trained neural network. But this trained neural network was for a homogeneous model, and therefore velocity is quite different. And it was, if you remember, a different source location. So even if we have a quite different velocity model and different source location, this idea of transfer learning can be used here. And as you can see here, it takes only about 10% of the computation time that it needed for the previous model. Therefore, this is a great advantage, and this is how we can really really improve the efficiency of our PINN eikonal solver, which is not available in conventional solvers like fast sweeping, as I mentioned in the beginning of this talk. And here are the travel time errors for the vertically varying TTI model. As you can see, again, despite using transfer learning, the accuracy of for our PINN model is much better than the regular fast sweeping method. And here are the travel time contours, which confirm this observation visually. And again, as you could see, that not only the velocity model is different, but the source location is different. Therefore, PINNs have this very attractive feature that you could train a model, and then once it's trained, you can use it for several different velocity models. And therefore, this is pretty attractive in the process of seismic inversion, where you keep updating the velocity model and you have thousands of source locations. All right, now let's test it on a challenging model, which is a portion of the BPTTI model. As you can see, this one has sharp layers and sharply varying tilt angle. So here we see the travel time errors. On the left is the PINN. As you can see, for most areas it is extremely accurate, whereas what we see here on the left is due to sharp variations in the model. And therefore, this is one of the challenges that we observe with PINNs, is that when you have a sharply varying velocity model or some other parameter in your model, then PINNs tend to struggle in terms of their accuracy. Still, the accuracy is much better than regular fast sweeping method, as we can witness here. And here are the travel time contours, which also confirm this. As you could see, that both the PINN solution is much better than the fast sweeping method. All right. To summarize what we have seen in this talk is that we saw how we can use neural networks to solve the anisotropic P-wave eikonal equation. One thing that should be mentioned here is that this method is mesh-free. Therefore, when you're training, you can randomly choose points within your computational domain. They don't have to be on a regular grid. And therefore we can also handle topography very easily. There are no special treatment needed when you have topography in your model, and sources and receivers do not have to be on a regular grid as well. So therefore this is one good feature compared to conventional techniques. All right, finally, we also saw how transfer learning can be used to significantly speed up our convergence, and therefore you could use on a variety of models, and this is particularly advantageous for seismic conversion. And since we're using TensorFlow at our backend, therefore there's very easy deployment of computations across a variety of platforms. Whether you're using CPUs, GPUs, the code remains the same. And if you have clusters, etc., you can still use the same architecture or the same code, I'm sorry. And therefore this is not the same idea that you have with fast sweeping, because for fast sweeping you need to write new codes for GPU, for if you want to use it multiple CPUs, and therefore this is really advantageous of PINNs. However, there are some challenges that need to be addressed, and these are really research open questions in terms of what we do in sharp heterogeneities. So this still need to be addressed, how you can optimize PINNs for sharp heterogeneities. And there are several hyperparameters that we saw. Again, tuning those hyperparameters really fast is again a challenging question that needs to be addressed. With that, I would like to end my presentation.